Hello, I am Rowan Grebeck, and I, along with Lakin Phillips and Jacob Pekaczyk, are going to discuss the process of generating electricity with hydropower and how we would use hydropower to power Ohio University. There are three main types of hydropower: dammed, run-of-river, and pumped storage. Dammed hydropower is what most people picture when they hear the term hydropower, a dam across a river. The benefits of this type of hydropower are that it works on many scales, and the power generated can be increased with demand by letting more water flow. The downside of this method is that its large impact on the environment and the risk associated with holding back so much water. Run-of-river is the most environmentally friendly type of hydropower. It does not dam a river, but instead diverts a portion of the flow to a turbine and uses the natural flow rate of the river to generate electricity. The downside of this technology is that the amount of power generated can't be controlled since the river isn't controlled. Pumped storage hydropower is the last type of hydropower. This method involves two reservoirs separated by a dam with a turbine. When power is needed throughout the day, water is allowed to flow from the upper reservoir down to the lower reservoir through the turbine, causing it to spin and generating electricity. When power is not needed and the cost of electricity is low, the turbine is spun backward, powered by that cheap electricity, so it acts as a pump, returning the water back to the upper reservoir where it can be used again. This technology has a balance of benefits and pitfalls. It has a lower environmental impact and also controlled power generation. There are three different types of turbines used in hydroelectric power generation. The type of turbine used is based on the amount of electricity being generated. The Pelton turbine is used for applications of up to 200 megawatts, where there is a large difference in height. This design consists of specially shaped buckets on a disc that fill with water to spin. Kaplan turbines are used in electricity generation of up to 400 megawatts. This turbine looks like a boat propeller with 3 to 6 blades that can be pitched differently for higher performance. The Francis turbine is used for generating up to 800 megawatts of electricity. This turbine is unlike the other two in that it uses axial flow. The cost of building a hydropower plant is very hard to generalize. We have discussed 3 different types of plants that will have different costs, and each type also comes in many different sizes. The most data exists for traditional river dams. Small-scale dams generating between 25 kilowatts and 500 kilowatts cost between $7.19 per kilowatt to build and $3.38 per kilowatt. On the large scale, a 500 megawatt power plant costs about $2,191 per kilowatt to build. Our goal is to power Ohio University using hydropower. According to the school's energy dashboard, OU uses about 20 megawatts of electricity per day, so that was our generation goal. When we looked for ways to power OU, we first looked at our local water sources. The Hawken River is what first came to mind, but after a few calculations, we determined it was not a feasible source. We then looked to Dow Lake. We decided we could create a lower reservoir, put a turbine in the existing dam, and create a pumped storage hydropower plant.
Ohio University uses a max of 20,000 kilowatts at one time. Using the theoretical power available from the falling water, where P is the theoretical power, rho is the density of water, Q is the water flow rate, G is the acceleration of gravity, H is the head, we've calculated with a 90% efficiency of 20,861 kilowatts. This is sufficient to supply Ohio University during peak demands. The capital cost for this project is somewhat low. Dow Lake Dam has been in existence since 1960. Therefore, the site preparation to retrofit the dam is only $2.2 million. The Pelton turbine and generator are quoted from an online resource. The power line calculation is based on the 6 miles from Dow Lake Dam to Ohio University and the price per mile. The pumping station is compared to a larger pumping station in Louisiana. We took the percentage of water we are pumping compared to the percentage of the water the larger station is pumping and came out with a cost of $31.5 million. The auxiliary systems include the hardware and software needed to operate and maintain the dam. The personnel cost is also included, which includes salary and the benefits. The total cost for this project would be $334.13 million. There are many risks associated with this type of project. We're going to look at the top 3 risks that threaten the integrity of the dam. The natural risk, such as flooding, landslides, high winds, and earthquakes, can damage the integrity of the dam. From an operations standpoint, improper maintenance and failure to open or close valves during high flow periods can also damage the integrity of the dam. The design of the dam is crucial. An inadequate spillway, internal erosion caused by embankment or foundation leakage, and improper design altogether with poor materials can cause the dam to have a catastrophic failure. Figure A has these risks laid out. Figure B shows the probability and the impact that each risk has associated with it. The management of this hydroelectric power plant has many responsibilities. To name a few, we have plant control, authority and environmental regulations, forecast, optimization, and interfaces. All of these need to be followed, monitored, and take proper planning to ensure that the plant maintains its operating efficiency and meets the demand for Ohio University.
Next, we are going to talk about policies pertaining to hydropower. The Department of Energy Organization Act, 1977, created the Federal Energy Regulatory Commission. FERC is responsible for issuing licenses and permits and performing inspections for all hydropower projects in the United States. Prior to issuing these licenses for hydropower projects, the environmental impact and economic benefits must be equally considered. Ohio Revised Code defines dam safety laws for the state of Ohio. Ohio Division of Natural Resources regulates administrative rules and supplements laws defined in ORC. Construction and alterations to existing dams requires a detailed plan to be submitted to the Chief of the Division of Water of the ODNR. Prior to altering the Dow Lake Dam, the effects on wildlife, fish, and public safety must be considered equally with the benefits of installing a hydropower system. Both the FERC and ODNR require periodic inspections of the dam to ensure the dam is operating safely. The ORC requires a detailed manual of dam operation, maintenance, inspection, and emergency protocol for Class 1 dams. Looking at the initial capital costs, estimated current costs to Power Ohio University, and the cost of operating the dam, which is primarily the cost to maintain the dam, we can determine the payback time. The calculated payback time is 16 years. After 16 years has passed, the total savings is $20.8 million per year. This estimation does not take into consideration any unexpected or emergency repair costs, but hypothetically the dam could be expected to operate with this amount of return indefinitely. In conclusion, by implementing a pumped storage hydroelectric plant at Dow Lake Dam, enough power could be produced to power Ohio University. The risks associated with using an existing dam are lower. However, environmental impacts the fluctuation could have on fish and wildlife are not known, and the structural integrity of the dam would require extensive research and monitoring prior to installation of the project. Permission and licensing to use a state-owned resource, specifically a state park used solely for recreational purposes for generating power, would be difficult.